Hello! Today I'm going to show you the advantage of Modelica language. We will try implementation of a simple system in 8 possible ways and show how variable Modelica is for such task. I chose an easy example of a mass, a kitten, on a spring system. For simplicity, we do not consider any damping or gravity yet. We are interested in the time course of the mass's position. First of all, we need to define the system. The properties of a mass, kitten, are governed by the Newton's equation. Force is mass times acceleration. Next, for the spring, we can write that the force is minus the spring stiffness times the position difference, that means the spring's elongation. And the fixed point just stays fixed at some position, for instance 0. Now we put it all together, where a is double derivation of the position and y1 is the fixed 0 point. Okay, now we know what we would like to simulate. Let's dive into it. At first, we are going to try the analytical solution. It is the most precise and usually the fastest to compute the time course, but it is not always possible to even found one. We will employ Laplace transform, and after a bit of work, we have the equation of the position of the kitten in the time. For complex systems, it is often impossible to find such function, so we switch to numerical methods. The first numerical solution of complex models have been implemented in procedural languages such as Fortran, C, etc. In these languages, the user is responsible for writing the solver as well. I would show an example of procedural implementation in MATLAB, where we can use implemented numerical solvers, for instance OD32. But first, we must prepare the function which we would like to integrate. We prepare the parameters, and we prepare the output vector. Now we have to solve the system equation for the derivatives and assign them the velocity and acceleration. And then we hand the whole function over to the solver function. And voila, plot the results. Nice. It still looks like a lot of work though. With Simulink, the simulation task becomes much easier. We don't have to write the code or care about the solver anymore. You just drag the items from the library. We come from the equation y equals minus k divided by m times y, so we need two integrators and a gain. But what does this mean? Where to read the resulting position from? Would you guess the position is here and the acceleration here? Very well. It is hard to see the spring underneath, right? This is how it was done in the history. Let's see how we do it now in Modelica. Here, I'm using the open source environment Open Modelica. However, there also exist professional tools such as Dassault Daimler, Wolfram System Model and several others. At first, we can use the legacy approach and duplicate the Simulink model. We use blocks from the Modelica standard library to recreate the Simulink model. Now, to set up the initial conditions. See? It works the same. But we are not using any Modelica advantages here. Let's try the equation-based approach first. We just declare the variables and write down the equation. This is really an equation though. We can change what is an input and an output. Quite simple, right? But what if we want to build a system of multiple masses? Kittens, in a series. In the previous cases, we would have to substantially rewrite the model. In the last case, it would be the least painful method, but still not optimal. Let's unleash the full Modelica potential for complex systems. We would start by creating a library of system components and a connector which interconnects the components. The connector contains one flow variable and one non-flow, so it acts as an electric wire, having both voltage and current. We would discuss the properties of connectors in later videos. We chose the position as a non-flow and the force as a flow variable. and draw some nice icon of it. First, we drag the connector in the scene and draw some icon of the component. Here we say that df equals m times a and an initial condition and a parameter. Here we say that y equals minus ky and a k parameter. Here we just declare that it's not moving and stays on 0. And now we join it all together. And don't forget about the initial condition. Voila! This is how we construct the models. Now what if we need to extend the functionality to double spring system? Without Modelica, it would be rather difficult. We have to add the equation solver for the previous solutions. With Modelica, we can just drag and drop out pre-made components. Look how easy it is to extend the model with another kitten in series. How would we do the double spring mass? I mean double kittens on a springs in Simulink. Well, it's still a very simple system though. And what about analytical solution to this simple system? No! No, 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 no! Of course, in most cases, the libraries are already prepared. Here we try the multibody from Modelica standard library. In fact, there is tons of open source as well as commercial libraries, from electrical powertrain systems through climatization of buildings to human physiology. We just set the spring stiffness parameter, the mass of the body, and choose the world with no gravity. And we can see the same curve as in previous examples. In commercial environments such as Daimler, the multibody library also provides 3D visualization. We showed several ways how to realize the mass spring system. With complex systems, the Modelica shows its advantages. The models are lucid and easily extendable. On the top of that, some tools from Modelica are open source and free to use. Try Open Modelica to get the feeling of Modelica possibilities. Thanks for watching and don't forget to subscribe.